Okay, so in this video, we are going to look at Euclid's division lemma. Now, the statement of Euclid's division lemma is here. It says, given positive integers a and b, there exist unique integers q and r, this is r, q and r satisfying this relation a is equal to b times q plus r, where the condition on the r is that it is greater than or equal to 0 and less than b. Now this is a mathematical statement of the lemma. Let us try to unpack this and understand what this really means. So let's take some examples to appreciate the intuitive understanding of this lemma. Now let's take one group, let's take three pairs of numbers. The first one is 17 and 6. Second pair of numbers is 5 and 12. And third pair of numbers is 20 and 4. Now what we need to do is we need to represent these numbers in the form of a equals bq plus r, where r has to be greater than equal to 0, but it should be smaller than the b. Okay, so this is kind of, as I said earlier, Euclid's division lemma. This is nothing but, it has to do with the long division, a different way of stating this. So let's see how it applies to the first pair of numbers. So we have 17. How can I represent it in this form? So a is equal to 17. Now b q plus r, that's what we need to write. Here b is basically the number 6. So we need to say a is 6 times what will give me a number that is closer to, so if I do 6 times 3, then it gives 18, so it's bigger than this. So I will just do it 6 times 2, that gives us 12, and 12 plus 5, that gives you 17, right? So if you look at the a equals bq plus r form, right, so we have this is b, this is q, and this is r, and this here is the number a. So what this means, you can also say that, q is the quotient, r is the remainder, and a divided by b, right? That's what we are trying to do. Now let's look at the other pair. 5 is equal to 12 times what gives you 5. Now we know that 12 is greater than 5. So the little trick here is you multiply 12 times 0 plus you add 5 to it. And this again is the form of a equals. So this is your a, this is your b, this is q or the quotient, and this is r as the remainder. So this is what we get. Now if we look at the third example, that is 20 times 4. Okay, so 20 equals, now we know that we can easily multiply 4 times 5 and it becomes 20, and you just need to add 0 to it to convert it in the form of, right? So you have a, 4 is b, the quotient is 5 or q, and the remainder is 0. So you can see that we have three cases over here. Okay, in the first two cases you can see that the remainder is greater than 0, and in the third case the remainder r is equal to 0. So what basically we have shown over here, that for any pair of positive integers a and b, we can represent them in this format of a equals b times q plus r, where the condition on r is that it should be greater than or equal to 0, but it should be less than b. B is the kind of the divisor. Okay, so that is the form of the lemma. Now I think it will be a good idea if you would like to try 3 examples for yourself. So if you take this number, first example is 10 and 3, second example is 4 and 19, and third example is 81 times 3. So why don't you pause the video and try representing these numbers in the form of a equals bq plus r. And what you need to remember is that the number r that you get must be either greater than or equal to 0, but it has to be smaller than b. So b is this number, second number here. So this is the b over here. Okay, so pause the video and kind of just have a look at this. So again, I just wanted to clarify that Euclid's division algorithm is simply a different way of stating the long division result, right? It has to do with the division of two numbers. And just to summarize what we said, the formula for that is, or the statement for it is, given positive integers a and b, there exist unique integers q and r which satisfy the relation a equals b times q plus r, where r is greater than equal to 0 and it is also less than the number b. So that is, in summary, the Euclid's division lemma.